E-stop circuits in industrial installations demand stringent safety requirements to guarantee reliability and effectiveness. These requirements primarily address single points of failure and the continuous monitoring of critical components. Firstly, e-stop circuits must be designed to prevent a single point of failure from disabling the system. Redundancy is a key strategy here. This can involve using multiple contactors or relays connected in parallel. The idea is that if one contactor or relay fails, the others can still interrupt the power supply to the equipment. Secondly, fail-safe components can be employed. These components are engineered to automatically revert to a safe state if a failure occurs. This ensures that the circuit will still function as intended even if a component malfunctions. Critical components within the stop circuit, including contactors, relays, and fuses, should be continuously monitored to verify their proper operation. Monitoring can be implemented through several methods. One method is periodic testing, where the circuit's functionality is checked at regular intervals. Another method is visual inspection, where personnel visually examine the components for signs of wear, damage, or malfunction. Redundant sensing elements can also be used to monitor the performance of critical components. For example, a second contactor can be utilized to monitor the operation of the main contactor. If the main contactor welds shut, which is a potential failure mode, the second contactor will detect this failure and trigger the system to shut down. Additional considerations for e-stop circuits include physical protection and clear labeling. E-stop buttons should be physically protected from inadvertent actuation. This can be achieved by enclosing the buttons in a locked box or providing covers to prevent accidental contact. E-stop buttons should be clearly marked and easily accessible. This ensures that personnel can quickly and easily activate the e-stop in an emergency situation. The e-stop circuit should be tested and certified to comply with relevant safety standards such as ISO 13849.1 and IEC 61508. Adhering to these requirements enables industrial installations to establish reliable and effective e-stop circuits. These circuits are crucial for safeguarding personnel and equipment during emergency situations. Single points of failure are vulnerabilities in a system where a single fault can cause the entire system to fail. In the context of e-stop circuits, a single point of failure could prevent the system from shutting down equipment in an emergency, leading to potentially hazardous situations. Several strategies can be employed to mitigate single points of failure in e-stop circuits. Redundancy, as mentioned earlier, is a primary approach. This involves duplicating critical components so that if one fails, the other can take over. For example, using two contactors in series to interrupt power provides redundancy. If one contactor fails to open, the other can still de-energize the circuit. Another strategy is to use diverse components. This means using components from different manufacturers or with different designs to reduce the likelihood of common cause failures. For example, using relays from different suppliers in the same circuit can reduce the risk that a manufacturing defect will affect all of them simultaneously. Fault tolerance is another important consideration. Fault-tolerant designs can continue to operate correctly even in the presence of faults. This can be achieved through various techniques, such as error detection and correction, or by using components that are inherently more robust. Monitoring of components is essential for detecting failures before they can cause a problem. This can involve using sensors to monitor the status of components and provide alerts if a failure is detected. For example, current sensors can be used to monitor the current flowing through a contactor and detect if it is not opening properly. Fail-safe design is a crucial aspect of e-stop circuits. Fail-safe design ensures that the system will revert to a safe state in the event of a failure. This can be achieved by using components that are designed to fail in a safe manner. For example, using normally closed contacts in the e-stop circuit ensures that the circuit will be de-energized if a wire breaks. Regular testing and maintenance are essential for ensuring the continued reliability of e-stop circuits. This includes periodically testing the functionality of the circuit and inspecting components for signs of wear or damage. Risk assessment is a critical step in designing e-stop circuits. A thorough risk assessment can identify potential hazards and help to determine the appropriate safety measures to implement. The risk assessment should consider factors such as the severity of potential injuries, the likelihood of accidents, and the reliability of the safety systems. Safety standards and regulations provide guidance on the design and implementation of e-stop circuits. These standards and regulations are developed by organizations such as the International Organization for Standardization (ISO) and the International Electrotechnical Commission (IEC). Compliance with these standards and regulations is essential for ensuring the safety of workers and equipment. Training and education are essential for workers who operate or maintain equipment with e-stop circuits. Workers should be trained on the proper use of the e-stop system, the potential hazards associated with the equipment, and the procedures to follow in the event of an emergency. Documentation is important for maintaining a record of the design, installation, testing, and maintenance of the e-stop circuit. This documentation can be used to verify that the circuit meets safety requirements and to troubleshoot problems. The documentation should include drawings, specifications, test reports, and maintenance records. Change management is essential for ensuring that any changes to the e-stop circuit are properly evaluated and implemented. Changes to the circuit should be documented and approved by qualified personnel. Security is an important consideration for e-stop circuits. The circuit should be protected from unauthorized access or modification. This can be achieved through physical security measures, such as locking control panels, and through cybersecurity measures, such as access controls and intrusion detection systems. Environmental factors can affect the reliability of e-stop circuits. The circuit should be designed to withstand the environmental conditions in which it will be used, such as temperature, humidity, and vibration. The components used in the circuit should be selected to be suitable for the environment. Human factors are an important consideration in the design of e-stop circuits. The circuit should be designed to be easy to use and understand. The e-stop buttons should be located in a prominent location and should be clearly labeled. The design should also take into account the potential for human error. Power supply considerations are critical for e-stop circuits. The power supply for the e-stop circuit should be reliable and independent of the power supply for the equipment being controlled. This ensures that the e-stop circuit will function even if the main power supply fails. The power supply should also be protected from overcurrent and overvoltage. Wiring considerations are important for e-stop circuits. The wiring should be properly sized and insulated to prevent short circuits and ground faults. The wiring should also be protected from physical damage. The wiring should be routed in a way that minimizes the risk of interference from other electrical equipment. Grounding is essential for e-stop circuits. The circuit should be properly grounded to prevent electrical shock hazards. The grounding system should be designed to provide a low impedance path for fault currents. Testing procedures should be established for e-stop circuits. The testing procedures should verify that the circuit is functioning properly and that it meets safety requirements. The testing should be performed at regular intervals and after any modifications to the circuit. Maintenance procedures should be established for e-stop circuits. The maintenance procedures should include inspecting components for signs of wear or damage, cleaning components, and replacing components as needed. The maintenance should be performed at regular intervals. Component selection is critical for e-stop circuits. The components used in the circuit should be selected to meet the specific requirements of the application. The components should be reliable, durable, and able to withstand the environmental conditions in which they will be used. The components should also be certified to meet applicable safety standards. Software considerations are becoming increasingly important for e-stop circuits. Many e-stop circuits now incorporate programmable logic controllers, PLC, or other software-based components. The software used in these circuits should be designed to be safe and reliable. The software should be tested and validated to ensure that it meets safety requirements. Cybersecurity considerations are also important for software-based e-stop circuits. The software should be protected from unauthorized access or modification. Cybersecurity measures should be implemented to prevent malicious attacks that could compromise the safety of the circuit. Integration with other safety systems is often necessary for e-stop circuits. The e-stop circuit should be integrated with other safety systems such as safety light curtains and safety scanners to provide comprehensive safety protection. The integration should be designed to ensure that the safety systems work together effectively. Emergency response planning is essential for any facility that uses e-stop circuits. The emergency response plan should include procedures for responding to emergencies, such as fires, explosions, and chemical spills. The plan should also include procedures for evacuating personnel from the facility. Communication is critical during an emergency. The facility should have a communication system in place to notify personnel of emergencies and to provide instructions. The communication system should be reliable and able to function even in the event of a power outage. Training on the emergency response plan is essential for all personnel. Personnel should be trained on the procedures to follow in the event of an emergency. The training should include drills to practice the emergency response procedures. Review and update the emergency response plan regularly. The emergency response plan should be reviewed and updated regularly to ensure that it is effective and that it meets the current needs of the facility. The review should include feedback from personnel who have participated in emergency response drills. Record keeping is important for e-stop circuits. Records should be kept of the design, installation, testing, maintenance, and modifications of the circuit. The record should be stored in a safe and secure location and should be readily accessible. Audits are an important tool for verifying that e-stop circuits are properly designed, installed, and maintained. Audits should be performed by qualified personnel and should include a review of the documentation, a visual inspection of the circuit, and testing of the circuit's functionality. Corrective action should be taken to address any deficiencies identified during the audit. Continuous improvement is essential for ensuring the ongoing safety of e-stop circuits. The facility should have a system in place to identify and address potential safety hazards. The system should include procedures for reporting hazards, investigating incidents, and implementing corrective actions. By following these guidelines, industrial installations can ensure that their e-stop circuits are reliable, effective, and compliant with safety standards and regulations. The goal is to provide a safe working environment for personnel and to protect equipment from damage in the event of an emergency.